If I do this right now, I can stop that in a second, but now you just see my screen, right?
Yeah.
Okay, good. Okay, I'll stop sharing for the moment. And I think I'll go 45 minutes at least, maybe a little more.
Yeah,
and
it's okay.
a lot of random thoughts. I put
So what's time right now there, Lawrence?
I,
Is it
I
10 o'clock?
I put more things in there than we talked about. I looked at my old notes back to you, and I
Yeah.
put it affected my thinking, and then I put so I'll cover a lot of different topics, some of which are related and some of them aren't. Oh, how come I can see myself twice? Okay, better not be able to see myself twice.
What
How
time
come
right now? Lawrence, what time right now there? It's 10 o'clock?
it's 9:53. It'll be 10 o'clock in a bit. Yeah.
Okay.
How come I can see two copies of you and me?
Yeah.
Someone is copying this. I don't quite understand it.
Yeah, we have another probably they put me as a co-host also.
Sensor Nano. Who's Sensor
Yeah.
Nano?
We're
Is
using the
that
Zoom from the IEEE Sensor and Nano Council of Malaysia.
in any case, okay, I don't know why there are two. I don't like seeing two versions but of me, but anyway.
Okay.
The delay. Oh, is that you doing that?
Yeah. Yeah.
Oh, okay. Well, if it's you, then it's okay. As long as you okay. Okay, well, people are coming in. So we'll wait a few minutes till it's 10 o'clock, right?
Yeah.
Okay, well, what I'm gonna do right now is just I'm gonna just stop my video. I'm just gonna well, I guess I'll keep my video on. I could stop video and then start it again so that I don't so people let me just stop video.
Yeah. We wait for another 5 minutes.
Yeah, so let
Yeah.
me just stop video. Okay, now
Okay.
you see a pretty picture of me, and I'll
Okay.
do some other things. And I'll come back on in 4 minutes.
Okay.
Okay. And I'm going to stop audio too so that I can do some stuff, okay?
Okay. Okay, Laura.
Right, where do I start? I know so little that I don't know what question to ask. That's how frustrating this is for me. I haven't got the language to ask you the right question.
Why we struggle in the world? It's not because we're trans. It's because other people fail to open their hearts.
Trump is not my favorite person, as you know.
Yeah.
But on North Korea, basically, I think he's doing the right things.
So, yeah, so we can work together through the right questions.
Right.
And the questions are the most important thing.
Right, where do I start? I know so little that I don't know what question to ask. That's how frustrating this is for me. I haven't got the language to ask you the right question.
Why we struggle in the world? It's not because we're trans. It's because other people fail to open their hearts.
Trump is not my favorite person, as you know.
Yeah.
But on North Korea, basically, I think he's doing the right things.
So, yeah, so we can work together through the right questions.
Right.
And the questions are the most important thing.
Right? Where do I start? I know so little that I don't know what question to ask. That's how frustrating this is for me. I haven't got the language to ask you the right question.
Why we struggle in the world? It's not because we're trans. It's because other people fail to open their hearts.
Trump is not my favorite person, as you know.
Yeah.
But on North Korea, basically, I think he's doing the right things.
So, yes, so we can work together through the right questions.
Right.
And the questions are the most important thing.
People are coming in slowly, 43 people.
Yeah, we also have a live streaming.
Let's see if it'll follow me. Oh, there it goes. Yeah, this studio microphone, this studio camera follows me. That's good. Anyway, I won't be up much because we'll have my slides until I answer questions.
Hi, good evening, Lawrence. Prabha here.
Hi there.
Hi. You okay?
I'm okay. Ready whenever you want me
Okay.
to be ready.
I'll just say my good mornings and good evenings and put in your bio, and then we're good to go.
Okay.
Okay. All right. Give me about 2-3 minutes. Okay. Salam sejahtera, selamat pagi, and very good morning to all gathered here virtually. We are here for International STEM and Innovation Colloquia Series-19, ISICS 19, thanks to the ever-increasing efforts of the tag team of Drs. Nazir Alif and Sharifah Nur Faiza. Thank you too to UNIMAP Vice Chancellor, Prof. Zaliman Sauli, and Deputy Vice Chancellor, Research and Innovation, Prof. Rizal Fandi, their respective officers and broadcast control team here led by Mr. Shah Rezan for hosting this event, as well as IEEE Sensor and Nanotechnology Council Malaysia for collaborating in this ISICS session. I'm Prabha, your moderator for this ISICS Series 19. Before we begin as normal, I would like to introduce our esteemed speaker for this Series 19, Prof. Lawrence Krauss. We wish you a very good evening, Prof. Prof. Krauss is an internationally renowned theoretical physicist, best-selling author, and acclaimed lecturer. He has contributed significantly to both science and also the public understanding of science. In the latter case, through his 12 popular books, including the international bestsellers, The Physics of Star Trek, and A Physics from Nothing. A Universe from Nothing, and his most recent book, The Edge of Knowledge, as well as his numerous appearances on television, video, and feature films. Prof. Krauss did his PhD at MIT and was then a member of the Harvard Society of Fellows before moving on to become a professor in the physics and astronomy departments at Yale University. Since then, he has held endowed chairs at Case Western Reserve University, Australian National University, New College of the Humanities, and Arizona State University. He is the recipient of numerous international awards for his research and writing, including the 3 major awards from all 3 U.S. physics societies, as well as the Public Service Award of the United States National Science Board. His research has spanned particle physics, cosmology, and astrophysics. In 1995, he proposed that most of the universe's energy resides in empty space, a prediction which was later observationally confirmed and which was awarded the Nobel Prize in 2011 for dark matter. He's currently president of the Origins Project Foundation, which aims to encourage curiosity about the world, connects science and culture, and connects the public to the people. Places and ideas associated with the greatest challenges facing humanity in the 21st century. He is also chair of the board of the Free Speech Union Canada, CEO of Gus Watch Productions, and hosts the Origin podcast, engaging with prominent figures from science, art, literature, and film. Prof. Lawrence Krauss has also held endowed professorship and distinguished research in addition to the above-mentioned institutions, appointments at Harvard University, Yale University, University of Chicago, Boston University, University of Zurich, University of California at Santa Barbara, Lawrence Berkeley Laboratory, and at CERN. Prof. Krauss this morning and his evening will talk about the relevance of physics in an AI world, a very timely topic with respect to the recent Nobel Prize announcements. Before we move on, Prof, I'd just like to ask you, would you like to be disturbed during your speech, or you'd like to be disturbed after for questions?
I don't know whether disturbed is the right way to put it, but I think I prefer questions afterwards if it's okay.
All right, that'll be
This
cool.
probably makes it easier.
All right, Prof, the floor is yours.
Oh, thank you. Well, it's a pleasure to be here, be there virtually. Of course, it'd be great to be there physically right now.
Yes, thank you.
But anyway, and then it would be morning instead of evening.
Yes.
And I appreciate all of you who are there getting up so early. It's a little early for this kind of subject, but I'll try and make it easy. I know it's a diverse audience, and I asked the organizers about that, and I don't want to be too technical. I also got some. The title of the talk is vague, which is good. I like vague titles. But I think the point. Well, I understand the point of it. So let me just continue to talk while I share my slides. So hopefully you can all see my slides. I like quotes, and Virgil is an author I like, and these are the tears of things, and the stuff of our mortality cuts us to the heart. Namely, what's the future of physics, and to what extent do we need to worry about fundamental science? One of the issues the organizers were concerned about is that we're focusing now, many people are focusing on applied areas and ignoring fundamental science. What's the point of fundamental science when there's so much you can do and so much money that can be made with using AI or other things to develop technologies? And I want to disabuse you of that notion. So that's what I'm going to talk about. So it's going to be some random remarks that are going to be all over the map, including some physics, because I can't give a talk without at least explaining some physics. And there may be physics experts in the audience, and if you are, then you can just enjoy it and sit back. But then I want to talk about some more basic ideas in a variety of areas. So let me give you a summary of, I think, the areas I want to talk about. First of all, I want to make it quite clear that technological innovation requires fundamental science. You can't do important technological innovation without making breakthroughs in fundamental science. The two go hand in hand, and there's a history of that. The next thing I want to talk about is the fact is that the GNP, the gross national product of the world, is due to curiosity-driven research, not applied research. And there's a lot of data in that. 3, I'll talk a little bit about quantum computing because a lot of people think it has something to do with AI. And I'll argue that, in fact, it'll produce a sea change in our ability to do quantum mechanics, but I don't think it's going to be the holy grail for changing the rest of technology, as I'll describe for the reasons why briefly. And all of these things, I hope, will provoke questions. I will argue that AI is good at answering questions and data mining, but that isn't physics. So I want to talk about AI and physics itself. The first few parts are talking about physics in a world where AI is changing things, but then I want to talk about AI and physics itself. And I want to deal with a question that people often ask, which is, will AI become conscious? And I'll talk about the challenges to that. I want to talk about consciousness because I spent a fair amount of time in my last book thinking about it. And I'll argue that even if AI were to become conscious, that I don't think it's the end of physics. And so those are the random areas I want to talk about, all related in one way or another to the question or the title that I was given by the organizers. So let's begin. If I can, okay. So I want to provide examples of the fact that the major technological developments in the world have required fundamental science. And this allows me to talk about some basic physics. And my first example is Michael Faraday himself. Michael Faraday created the modern world. He was my favorite experimental physicist of the 19th century. And his experiments in his laboratory basically produced the technology that's responsible for everything that's happening tonight. The technology of electromagnetism and utilizing electromagnetism to produce energy, light, and signals. So, but he didn't develop his laboratory with that in mind. His laboratory is full of interesting and obscure experiments, and they're famous examples of some of the stories are apocryphal, no doubt, of the Prime Minister or Queen Victoria coming in his laboratory and seeing jumping frogs and other things and asking, what use will any of this be? He gave 2 answers that I know of, and I'm not sure he really did. These are stories. One of them he's claimed to have said to Queen Victoria. He said, of what use is a newborn baby? But to the Prime Minister, the answer he gave was more relevant, I think. He said, of what use is any of this? Well, one day it's so important that you'll tax us for it. And in fact, that is exactly what happened. His development of the connections between electricity and magnetism produced, of course, the ability to generate energy and power and motors and lights and all the things we now get taxed for. But even then, it's interesting that his development of this technology, that his development of the ideas that led to the technology, was still very fundamental. Faraday wasn't an educated man. He didn't have any formal education. He was a bookbinder's apprentice. And he went to the lectures of Humphrey Davy, the head of the Royal Institution. And what he did was he took wonderful notes, and then he bound them in a volume, and he presented it to Humphrey Davy and asked if he could be his assistant. And with the beautiful notes, Humphrey Davy said yes, and eventually Michael Faraday rose to become the head of the Royal Institution. This is the first important lesson for the students out there, and I saw some people who looked like they were students early on. Always suck up to your professors, because you never know where it'll get you. And in this case, taking good notes got him there. But more importantly, he couldn't do the algebra behind electromagnetism. And so he had to invent a picture in his mind of how to understand the electromagnetic forces and electric and magnetic forces. So he developed this picture where he thought of an electric charge as having lines go out of it. He called them field lines. And he said, well, an electric charge creates a field, and a charge that's bigger will create more field lines, and a charge that's bigger still will create more field lines. And that picture allowed him to understand the repulsion between like charges and unlike charges, with the recognition, as he said, that the field lines can't cross. Then like charges the field lines would produce repulsion, and unlike charges, the field lines could then go out from one charge and into another. And in fact, this allowed you to reproduce pictorially exactly the mathematics of electric fields and electric forces. He invented this idea of an electric field was just an invention of his mind, a crutch, if you wish, to help him understand what was going on in the laboratory. They were just a mental development, nothing to do with reality. But of course, what happened was that led the greatest theoretical physicist of the 19th century, James Clerk Maxwell, to use the results of Michael Faraday and to ultimately show that fields were not just an invention of the mind, but were real. What Michael Faraday had discovered by accident in the laboratory was known that an electric current produces a magnetic field. That was known. So electric charges, when they're moving, can produce a magnetic field. People therefore wondered, well, could a magnetic field produce an electric field? And people would take strong magnets near wires to see if they could get charges to move, and nothing would happen. Faraday discovered by accident, by having an electromagnetic in one end and a current and a wire in another end, that by turning on the electromagnet, when the magnet turned on, suddenly a current flowed in the nearby wire. And what he discovered, which is of vital importance, was that a changing magnetic field can produce an electric field. We knew that a changing electric field, namely a current, could produce a magnetic field. And this was what Maxwell codified in his 4 famous equations that physics students now wear proudly on their t-shirts, the 4 Maxwell equations. But that led to something important, because Maxwell realized that if a changing electric field produces a magnetic field and a changing magnetic field produces an electric field, then you could do something. If you took a charge and shook it, you'd produce a changing electric field that would produce a changing magnetic field. But if it was constantly moving, then that changing magnetic field would produce an electric field. And effectively, what you'd produce is a disturbance that would travel out in space. A disturbance of these fields, electric and magnetic fields, which less than a generation earlier hadn't existed, and they were invented in the minds of this experimentalist, Michael Faraday. But the great thing that he did was the wonderful calculation that Maxwell did, and it's one of my favorite calculations to do in undergraduate physics, is to show that you can calculate the speed of that disturbance just in terms of 2 fundamental quantities: the strength of the electric force between 2 electric charges and the strength of the magnetic force between 2 magnets. If you measure them in the laboratory, you could calculate the speed of that disturbance. And what did Maxwell find? He found out that the speed of that disturbance was nothing other than the speed of light. He discovered that light was an electromagnetic wave. And that was a profound discovery. Profound in many ways, not because, of course, the nature of light had not been understood for a long time, but it was that fact that the speed of light could be calculated from fundamental constants of nature that ultimately had another effect. It inspired this guy here, Albert Einstein, who was thinking about light. And I'm not going to go, for lack of time, I'm not going to go into the beautiful way that Maxwell's result led him to realize something. It led him to realize that the laws of physics were not consistent. The laws of Maxwell could not be made consistent with the laws of Galileo unless the speed of light was constant for all observers, regardless of their motion. And I'd love to spend time showing you that. It's only about 10 minutes, but I don't want to spend the time now. But when he realized that that the only way you could take Maxwell's result, that the speed of light could be calculated from these fundamental constants of nature, and therefore itself must be a constant. And the only way you could make that consistent with the laws that Galileo and Newton had developed was if the speed of light was a constant for all observers. Even if you're running towards a light ray, you measure it to have the same speed relative to you, even if you compared to whether you're running away from the light ray. it always looks like it's coming at you with the same speed, regardless of your motion. Something that's very non-intuitive and seems crazy. And the only way he could reconcile that with the measurements of distance and time were if distance and time were relative. And he came up with that by thinking, and I want to point out that there is a fundamental relationship between technology and ideas. His understanding of time came up from the result of, the examples he used were trains. These are trains in Basel, Switzerland. I've spent time in Switzerland. I've written at least one of my books over the many summers while I was spending in Switzerland. And before I had an iWatch, I could keep watch by the trains in Switzerland, and they're famous at being always on time. Now that's important because it's rather interesting actually how technology changed the notion of time. And I'll take a little aside and mention this. Until trains existed in Europe and throughout Switzerland and the rest of Europe, every city had its own time zone. Every city kept its own time zone. And that was okay, because if you were traveling by horse and cart, the time it'd take you to get between cities was such that the difference in time zones wouldn't affect you. But once the trains were developed and you could rapidly go between cities in Europe, it was clear that you needed a single time, because trains would go so fast between cities that you needed to synchronize clocks in different cities. And the synchronization of clocks and trains was something that became central to the way Einstein thought of relativity. After all, when he was a patent clerk in Bern, what did he look up at but the beautiful clock at the center of the city and the train stations around him? And he developed his understanding of relativity in terms of clocks and trains. And I'm not going to go into it, but the three consequences of relativity are that if I'm moving very fast with respect to you, lengths contract. My ruler, this pen, would look smaller, so you can see me in the upper corner, would look smaller to you if I'm running relative to what it would look like to me. And people somehow think this is perception, but it's not. My ruler would be smaller. Every measurement you could make of my ruler would tell you it's smaller for you than it is for me. Simultaneity would go out the window. Events that are simultaneous for me in different locations would not be simultaneous for you. And also time would dilate, the most important feature. That if I'm running with respect to you, my clocks will appear to tick more slowly relative to you. Now these were all developed before there was any technology to measure any of this. It was just esoteric ideas. We now can measure all three of those things in an undergraduate physics laboratory, but there was no technology at the time that could measure any of those things. But Einstein went further and created his greatest success. But before he did, I should say, probably relevant to his greatest success, one of his teachers, perhaps the only teacher who didn't hate him, was a teacher named Hermann Minkowski, was a mathematician. And 3 years after Einstein developed his ideas, Minkowski wrote a paper saying, henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. And what he realized with these strange results from Einstein told us that space and time were not separate, that space and time were tied together in a four-dimensional space we now call Minkowski space. That space and time, one person's space could be another person's time, and vice versa. And again, I won't go into this, but it was a profound development, a pictorial development that was essential to Einstein's next and his greatest discovery. His greatest triumph was his theory of general relativity. And you could write it down mathematically in this way. The left-hand side of Einstein's equations relate to the property of space and time. The right-hand side of Einstein's equations relate to the energy and momentum. And what Einstein showed is not only will motion change space and time, but energy will change space and time. Energy can curve space. This most beautiful development and certainly one of the most esoteric developments you can make, because we can't see curved space. It doesn't appear to impact on us in any daily life, but space and time are affected by energy. So this was one of the most beautiful developments in the 20th century, his theory of general relativity. And most people would say, great, but it's very esoteric. But I want to point out, and here, this is the reason I introduced this long history, is it's vitally important to modern technology. And we couldn't have a technology which is essential. Every one of us uses it every day. That technology could not have been developed without this theory. And the technology relates to the fact that time depends upon where you're standing. This is the Harvard Physics Laboratory where I used to have an office when I was at Harvard. It was facing the back of this building, not the front. The Jefferson Physics Laboratory is a Lyman Physics Labs that were both here. But you notice a little cage, a little thing that was built on top. That was built on top to do an experiment by Robert Pound and George Rebka, Pound's student. They realized that relativity told you that clocks would tick at different rates in a gravitational field. And in the bottom of the Harvard Physics Laboratory, you're closer to the center of the Earth than the top of the physics laboratory. And they realized, and it's an amazing experiment, that you could actually do an experiment that would measure the change in the rate clocks ticked in the bottom of the lab versus the top of the lab. The challenge to them was to measure a shift that was predicted by Einstein to be smaller than 1 part, well, about 1 part in a million billion in the rate at which clocks ticked. And you might think that's impossible to do, but the technology was developed that could do this experiment, technology that was later relevant to what I'll show you next. And that experiment was done. It was before the internet. So Mr. Pound and Mr. Rebka, that's Robert Pound on the right, he was sitting on the top, and Rebka would do it, set his radioactive source in the basement, and they talked by telephone in the old days, and they did the experiment, and they showed indeed that clocks tick at different rates, that Einstein was correct. Now, again, this seems like an esoteric experiment done at Harvard University to prove something, a prediction which is esoteric and may be relevant for the universe, but certainly isn't relevant for humanity. But as I say, every day, every one of you depends on this. Because GPS systems would not work without, if we just built these detectors and used what is common sense, we'd come up with the wrong answer. How do GPS systems work? They work by a series of satellites that are up 8 or 10,000 miles above the Earth's surface. Now, the way they work is quite simple. You have your phone and a clock there, and what you can do, what your phone will tell you, there are atomic clocks on these satellites, very accurate atomic clocks, and they'll determine the time when a signal was sent out, a light ray or radio wave was sent out that's received by your phone, and your phone receives it at another time. Now, so therefore, you can determine the time difference, the time it took for that signal to propagate from the satellite to your phone. Well, if you have 3 satellites and 3 different measurements of those times, you can triangulate and therefore determine, if you knew the satellites were, exactly where you are. You need 3 of them to do it, which is why if you're old enough, like me, you may remember in the old days of GPS, it would begin to say, looking for satellites, and until it found 3 satellites, it couldn't tell you where you were. Okay, now all that happens much quicker. Great. Very simple. The time it takes is the distance, is the speed of light, the distance that it goes is the speed of light times the time it takes to get from there to there. So the distance, you measure the distance traveled by the speed of light times the time, and the time, therefore, the speed of light divided by distance. And all of it should work out classically. An undergraduate physics student should be able to do this. But there's a problem. And the problem is it won't work. And it won't work if we didn't know about general relativity and special relativity. Remember, these satellites are moving very fast. Einstein told us that if you're moving fast relative to me, your atomic clocks will tick at a slower rate. And we can work out, given their speed, that in a day, they'll be slower by 7 microseconds compared to the clock on your phone. But that's a small change. It turns out general relativity produces a bigger change. The fact that those clocks are high up above the Earth means they're in a smaller gravitational field. The gravitational field is a little bit weaker where those satellites are. And you can show that that will cause those satellites to be moving, the clocks in those satellites to actually be ticking faster than the clock on Earth by 45 microseconds per day. The net result is that the clocks are in space will be ticking at 38 microseconds per day faster than your clock on Earth. Now, light moves 1 meter in a nanosecond, roughly. 3 meters in a nanosecond, actually, but it doesn't matter. That means if these clocks are ticking are out by 38 microseconds, then the distance you would calculate where you are would be out by 38 kilometers in a day, or 1.5 kilometers in an hour. If we didn't take into account this esoteric fact of relativity, general relativity, which you might think has no bearing on what we're doing on Earth, then this simple technology, which actually sophisticated technology, would not work. In an hour, you'd already your GPS would take you to the wrong place by 1.5 kilometers, and none of us could function nowadays because all of us use GPS to get where we're going. That's one example of how new technologies require fundamental science. Fundamental, not applied science. There are other examples, and well, let me give you an example that I had to deal with. I wrote a book about Star Trek, as you've been told, and I went to NASA one day and for a meeting where all these engineers were trying to develop warp drives, and I had to convince them that the question of warp drives was not a question of engineering. It was a question of fundamental physics. To develop a warp drive, we'd have to answer questions of the universe that we don't have the answers to now. Therefore, no engineering is going to help until we know whether you can produce the right kind of energy that'll produce a warp drive. And it's even more important for things like time machines. It turns out time machines may be possible given general relativity. This is an example of a time machine. It's a wormhole and that connects two otherwise distant places in space. And I'm not going to go into how this can be a time machine. The first person to show that a wormhole could be a time machine was Kip Thorne, by the way, who later on won the Nobel Prize in Physics for developing gravitational waves. But if you could create a wormhole, you could produce a time machine. And it's remarkable. But the answer is, can we create wormholes? Well, that's the question. The answer is we don't know. We don't know the physics of whether you can create the right kind of energies and momentum to create a wormhole. And until we know whether that's even possible, we don't know whether you can create time machines, much less warp drives. And those forefront technologies that you might like to do if you're an engineer will require us to know about fundamental physics in a way we don't know now. But here's a more practical example. The internet. Particle physicists are looking at the most obscure aspects of nature, trying to understand the fundamental forces that govern matter and energy at the smallest scales. To do that, we built huge accelerators. And that's the problem. This is, you can see one of the large detectors at CERN, at the Large Hadron Collider. I think this is a CMS detector. And these are the detectors that we later on used to discover the Higgs particle. Great. But you can see that they're pretty big. But more importantly, it takes a huge team to develop. This is the single collaboration for the CMS detector, I think. And it's actually not even the whole collaboration. But this was the challenge. When this detector was being built, and in fact the detector before that at the Large Hadron Collider, what was before that, LEP, you had thousands of physicists coming in on a single experiment, and they'd all bring their computers with them and analyze data. But the problem was they'd analyze the data on their experiment, and then how could they communicate to other experimentalists? And if the data was so immense that you couldn't store it on a single machine. So someone had to come up with a way that 1,000 physicists could look at the same sets of data, independent of what machine they were working with, and communicate to others without walking to the laboratory and showing their computer. It was a problem which was insurmountable without a special kind of new technology, a new software technology. And of course, Tim Berners-Lee developed a software just for use by those experimentalists, so that they could communicate with each other and independent, invisible for whose machine was doing what. They could transfer information between machines, and they could all access information that wasn't on any machine. To do that, he developed what he called the World Wide Web at the time, which was a World Wide Web for experimental physicists. But it quickly got taken over and became the internet. And perhaps nothing has changed modern society more than the internet. But it wouldn't have been developed were there not the need. Necessity is the mother of invention. And the need was the most obscure experimental work that humans can do, which is at the Large Hadron Collider. So that interweaving between modern technology and fundamental physics is clear. Okay. I want to just, in the next step, I want to just tell you briefly about the value of fundamental research as determined by large groups in the 1990s. I think that's when I was involved in this. There was a report commissioned by the U.S. government called Rising Against the Gathering Storm, which was what should the U.S. government do to remain technologically competitive. And that report, looking at things, analyzed, it said the prosperity the United States enjoys today is due in no small part to investments in the nation has made in research and development at universities, corporations, and national laboratories over the last 50 years. In fact, as an old friend of mine, Bob Solow, who's a Nobel Prize-winning economist, showed, the economic value of investing in fundamental science and technology has been thoroughly investigated, and published estimates of return on investment for curiosity-driven research, not applied research, range from 20 to 67%. Most investors would be thrilled with that kind of return. And in fact, later on in the report, it was argued that 50% of the gross national product of the United States was due to investments in fundamental, curiosity-driven research a generation earlier. And that's the point. If we only invested in applied research, we would, take computers. If we'd invested in better, faster computers, applied computers, when computers were first developed, we'd be developing wheels and pulleys that would be faster and faster. Instead, what happened, the transistor got invented at Bell Laboratories and changed the way computers can be made. I think I probably have a few examples. That's from the National Academy of Sciences report. But it's more than that. If you think about computers which have changed the world, they changed the world because of Moore's law keeps getting better. The fact that there's a doubling rate in both storage and computer speeds. Every 6 months, they roughly double in the amount of storage and speed you can do. People thought this Moore's law would have to end. It hasn't yet ended, over 40 years since Gordon Moore first proposed it. Why? Not because we're trying to do applied research, but because the fundamental physics of materials has developed so that the objects on which are the fundamental bits of computers, from magnetic tapes to electrons and etc., that the fundamental material science has developed in a way that Moore's law could continue. You could store more things on smaller devices, not because you were plugging ahead with the same technology, but because the physics allowed you to use new technologies to store and manipulate information. Then to present it, we all used to have monitors that were cathode ray tubes. The first thing that happened was the development of charge coupled devices to store information, again, requiring new physics of materials. Then LEDs, then LCDs, liquid crystal displays. All of that required new materials. In fact, the Nobel Prize in Physics was given to the person who first developed blue LEDs, which was, if you're going to have red, green, and blue, you've got to have blue LEDs if you want to have the computer screens that you're watching me on now. And so all of this required not applied research, but fundamental developments in physics. And that's not going to change. And that's what I want to stress. We have to keep pushing physics at its fundamental stage. Now, I want to now jump, because I want to talk about AI and physics per se. And a lot of people somehow think that quantum computers are going to dramatically affect AI, produce AI, or are going to dramatically affect society and technology in a way. there's a lot of hype associated with quantum computers, and quantum computers are remarkable. But I think that the claims of what they're going to be able to do are overrated. They will do remarkable things, but you know what they'll do remarkable things for? For physics, in my opinion, more than technology. The reason a quantum computer is useful is that classically, if you have n objects around the room and you want to determine their state, you require n real numbers, where they are, or what their momentum is, or things like that, or n pairs of real numbers, let's say. But a quantum mechanical state is more complicated. That state we describe by this notation where every object, which can be a qubit, every quantum mechanical object, which could be, say, 1 or 0, can have a state, and let's say we have a certain number of them. Every object can have a state of 1 or 0, but quantum mechanically, the system is in a superposition so that though you have 2 to the n states, every say electron can have its spin up or down. And to describe that all the different states of the system, if each object in the system can have 2, can be up or down, and all these things are independent. To describe all the different configurations of that system, you'd require 2 to the nth states, not n. Now, what's important is that quantum mechanically, systems are in superpositions of those 2 to the nth states. Namely, a quantum mechanical system can be in a superposition of all of these different microscopic states. Classically, if you want to describe the quantum mechanical system, therefore, you have to calculate the probabilities of all of those 2 to the nth states. And when n is a large number, there are many, many states, and classically it becomes impossible to numerically solve the Schrodinger's equation and numerically calculate the states, the probabilities for all 2 to the nth states of even a system with 50 particles has 2 to the 50th states, and that's probably beyond the system, the ability of most computers now. So great. Quantum computers may allow you, therefore, to probe those systems, those states. A quantum computer is useful because if it has n qubits and quantum mechanical objects, which could, say, be in 2 states, 1 or 0, the quantum state of that system can be a superposition of all of those states. So the computer itself is in a superposition, the very superposition that you want to try and calculate classically, or at least simulate classically. And therefore, if you measure that quantum mechanical system, this quantum mechanical system will tell you the values of a set of 2 to the nth complex numbers. So the computer gives you a quantum simulation of a quantum system because it's in a quantum state. And that's why Richard Feynman was first interested in quantum computers, because basically the computers internally in a quantum mechanical system is a quantum mechanical system and is intrinsically therefore probing all of the quantum mechanical Hilbert space, or at least the phase space of the allowed system. Now, that's why quantum computers are interesting, because in principle, and I'm not going to go into the details of therefore how you measure and all of the rest, that's a classic quantum computing. But what I want to point out is the problems and why these systems will be useful for physics more than they will be for, say, developing new code breaking, for example. The problem is all of these spins are entangled. That means that the system is in a superposition of all of those states, and those states are entangled with one another. That requires the system to be incredibly isolated. The reason we don't feel like quantum mechanical objects, the reason we don't behave quantum mechanically, is that there's lots of noise. All of the particles in our body are interacting under a heat path and colliding, and there's light coming in, and in order to maintain that coherence that is so essential to the system remaining quantum mechanically, you have to keep the system incredibly isolated. That's very hard. And the more qubits you have, the harder it is. And that's why now systems have maybe been up to 50 qubits, but they can only preserve that isolation for fractions of a second, small fractions of a second. To break codes, the kind of codes that are used to store the information in your credit cards, you probably require maybe 70 to 100 qubits, more than we're able to manipulate right now with quantum mechanical computers. But it's just a matter of time before we'll get a little bit better and a little bit better. But even when we do that, the point is, it's already been shown you there are classical ways to make unbreakable codes. So it's not as if that once you have a quantum computer, suddenly you'll be able to break the codes of the world financial system. Already there are codes that are already being developed that quantum computers won't be able to break. So that give and take of the technology of quantum computers and how they'll impact on the financial world is dubious at best. But where it isn't dubious is in trying to understand quantum mechanics itself. If you take 20 atoms in a molecule, there are already 1 million complex numbers that must be calculated classically to manipulate that system. If you have a molecule of 40 atoms, then you have 2 to the 40th, which is a much bigger number. But a quantum computer can simulate that molecule because it itself basically behaves quantum mechanically and allow you to probe the behavior of that molecule. And so when it comes to quantum chemistry, there's already, even with 5 qubits, there's already work that's being done at the forefront of physics to describe small molecules and their quantum mechanical behavior. And where quantum computing will become clearly useful is in understanding the fundamental science of molecules. And that's the kind of physics that excited Feynman when he first proposed quantum mechanical computers, because the computer will solve the quantum mechanics in a way that a classical computer couldn't, and allow us to explore quantum mechanical systems and their behavior in a way that we couldn't possibly do, and therefore understand the quantum world better than we do now. And of course, that'll ultimately produce new technologies, because when you can do even larger molecules, you might be able to look at proteins and folding and the technologies of creating new things like that. But to do that it involves understanding fundamental quantum mechanics, not just applying it immediately to code breaking and banks. So I think in the lifetime of many people in this room, quantum computers will become incredibly important for understanding fundamental science, which then can be used to develop new technologies, but not directly, in my opinion, to develop new technologies. Maybe I'll be wrong. We'll see. I try normally not to make predictions, except for predictions that are 2 trillion years in the future, where no one can test my predictions. What are the limits of AI? I want to end with this sort of limits of whether AI and consciousness. Who knows? We don't know what the limits are because we don't know where AI is going to go. But, and here's the important but, I think AI is intrinsically limited in what it can do. One of my favorite quotes is from a book called The Peregrine, which is about a peregrine falcon. And the guy said, the hardest thing of all to see is what is really there. And that's the heart behind science. And there, AI will have a huge impact. AI is going to change what we can see when we look at systems. But acting on what we see will require understanding. And that understanding may be beyond AI. And so let me just try and explain exactly what I mean. AI and neural nets, the things that won the Nobel Prize in physics, are very good at doing a few things. They're very good at pattern recognition. Neural nets assign basically a weight to different ways of examining a system and different ways a system can evolve. And by looking at different weights and optimizing that, you can look for patterns in a way that is fast. And it's the reason that I just took a Waymo car in Phoenix. That's the reason I can go in a car that's self-driving. It can recognize the patterns very fast around it and see whether it's a person, a car, a stop sign, or something else. It can also filter information very fast, faster than humans can do. And it can predict outputs faster than humans can do. And that's why filtering information, that's why ChatGPT seems so remarkable, because it can take information from the whole internet, filter it, and try and answer a question that you might ask by filtering it. And it does that by predicting the output word letter by letter for what's going to happen next by looking at filtering information that's been put into it. So AI is remarkably good at answering questions. But I would argue that physics requires asking questions. And asking the right questions requires a very different skill set than pattern recognition and filtering information. Those are helpful. But asking the right questions is something that is central. And I simply don't know when AI will be able to ask the right questions. I know it can answer the right questions now. And to understand what AI can do, I want to talk about ultimately consciousness and AI. Part of the problem of consciousness comes from a quote from a famous physicist, Erwin Schrödinger, who said, "Consciousness is a singular of which the plural is unknown." Namely, we don't know what consciousness is. We have one example of consciousness, humans. My two dogs are sleeping here. Actually, they're not sleeping. They wish I was down there playing with them right now. They're looking up at me. And they look up at me plaintively, and I don't know if they're conscious. I like to think they are, but we don't know if they are. And what I want to point out is we know so little about consciousness right now that it's hard to say if computers are going to become conscious. We don't even understand our own consciousness. Most cognitive scientists actually steer away from a very definition of consciousness. Instead, they try and explore different features that we can see using evolutionary considerations. But unlike legs or fins or other things that evolution has helped us study, we cannot objectively measure the cognitive developments of a long extinct species. So even trying to understand the evolutionary development of consciousness is essentially impossible right now, because you can measure the many facets, even the DNA of ancient objects, but their cognitive developments we can't see. And even in extant species, even in species like my dogs right now, there are no direct probes of consciousness. You might think we can probe consciousness by probing their behavior, but probing behavior is not probing consciousness. I had a quote from Bertrand Russell, but the bottom line is that an amoeba avoids certain negative stimuli from acidic systems and heat, but amoeba don't have neurons. They're not conscious. To try and infer consciousness from behavior is a very slippery slope, and I want to just give you an example of how slippery it is for humans, because I love this example, so it gives me a chance to use it. We all feel like we have a self that's inside of us. Many philosophers claim that self is an illusion. And like most of what philosophers say, I don't care about it, because I really care about, I clearly have my sense of self. Whether it's an illusion or not, if I get kicked in the shins, I feel it. If I get jilted by a lover, I'm torn apart. What really matters is not whether it's an illusion, but how that illusion arises. That's what's of interest to a scientist. Just like the illusion of solid objects. My desk is solid, but we all know it's mostly empty space. The question is, how does that solidity arrive? And we don't know. We don't know what combination of things creates that self-awareness. We're nowhere near it in humans, much less in AI. And we don't even know if it's the right question. We don't even know if self itself and self-awareness is the key facet that's important for consciousness. One of the things I just want to point out, for one of the reasons why a computer sitting at your desk is unlikely to become conscious, is if you look at the evolutionary basis of consciousness, there's a huge literature that suggests that homeostasis is probably an essential part. Systems learning how to preserve and measure their state and keep it relatively static in the presence of an environment that might get hotter or colder. To do that, you have to probe the environment. You have to have nerve systems that a nervous system that doesn't just calculate, but actually receives information from the outside world. And so interacting with the outside world and sensory systems are probably an essential part of what may eventually be conscious. So I want to just point that out as a caveat. But But I want to point out even for humans, we can't trust our own consciousness. And the example I want to give you is a beautiful one that's so wonderful I can't resist it. It involves an experiment that was done in the, I think the 60s or 70s by Michael Gazzaniga and a colleague. Epileptic people who have epileptic seizures, it was discovered that you could reduce their seizures by cutting this corpus callosum in the center of the brain. The brain is two hemispheres, the left hemisphere and the right hemisphere, and they communicate through this corpus callosum. If you severed it, it turned out epileptic seizures would be decreased, but there wouldn't be any real other, significant cognitive problems. You could function. But that gave the experimentalists a beautiful test subjects, because you could now, what Michael Gazzaniga and his colleagues did is they'd put subjects in, and they'd have a barrier, a wall, basically, and people would put their eyes against the wall, and the left eye would see one thing, and the right eye would see another thing. And so what's interesting, of course, is that when it comes to the visual field, your left visual field is governed by the right hemisphere of your brain. The right visual field is governed by the left hemisphere of your brain. Similarly, for body control, the control of your hands, your left hands, and what they're doing is done in the right hemisphere, and similarly, the right hands are controlled in the left hemisphere. But speech is processed only in the left hemisphere. So they did the following experiment. They put people in those boxes where there was a barrier separating the left and right visual fields, and they showed two pictures: a snow scene and a chicken's claw. And then they said, okay, then they gave people objects, little miniature objects that they can manipulate with their left hand or their right hand. And when the people saw that, well, one of the objects that people did with their left hand that would be similar to the scene they could see in the left was a snow shovel. And similarly, in the right, there was a little model of a chicken. So people would get, they'd see with their left eye, and they'd see a snow scene, and they'd look down, and then their hands would move, and they'd get the shovel, and then they'd do the same thing with the right hemisphere. But then they asked the subjects why they did that. Now remember, their speech is only governed by the left hemisphere. So when they talked, that left hemisphere, the speech had no idea what they were seeing in the right, what they were seeing. I'm sorry, what they were seeing in the left hemisphere. Because remember, the visual field in the left hemisphere is controlled by the right part of your brain, and the right visual field is controlled by the left part of your brain. So they couldn't see what was going on. They literally, your speech would not be able to tell you that, was not connected to the fact that you were seeing a snow scene. So they said, the chicken claw goes with the chicken, and you need a shovel to clean out the chicken shed. So these people were giving conscious arguments for why they were doing things, which was completely unrelated to why they were actually doing things. But their vocal consciousness gave a perfectly rational explanation for why they were doing things that had no connection at all to what was actually happening in their brains. So even in the human brain, when we try and probe human consciousness, we're not probing consciousness, because we're asking subjects what they're seeing and what they're doing. That may not be related at all to what's happening. So, as Richard Feynman once said, and you'll be pleased to know I'm coming to the end of this, I figured I'd go for an hour, and then we'd have questions. He said, if you can't build it, you don't understand it. Well, that's more or less what he said to me once. And what he really said, he said to me, this was on his blackboard when he died. People found it on his blackboard. I remember him saying once to me, he who can do nothing knows nothing, a similar version of this. But my point is that we may ultimately only learn about consciousness by developing computers that may one day be conscious. So AI may indeed one day be conscious. I don't see an impediment to that. I think it's going to be a long time coming. But even if it does happen, will it end physics? That's the last question I want to ask. And my point is, no. People think that an AI world, a conscious AI world, is suddenly going to be the world of the Terminator or some dystopic science fiction movie. And I want to give you an object lesson to how a new technology that was developed once that people thought would end the world didn't end the world. It happened in the 9th century and 8th century and 7th century BC. In the 9th century BC, the Phoenician alphabet was introduced into Greece and it evolved over the next few hundred years into writing. And that was viewed as being a disaster. Philosophers said that writing would be the end of literature and drama because it would cause people to, Plato said, writing was an impediment to wisdom because it does not capture the whole truth and it propagates the illusion of knowledge and would eliminate the need for memory. Stories used to be told orally, and you had to remember it. And if you write it down, you didn't have to remember it. So people basically said this new technology of writing was going to end storytelling and end literature and end wisdom. And that was in the 7th century. Even Socrates said he was suspicious of writing. He argued that written communication would never be as clear as face-to-face communication because one couldn't ask questions of a document. A true statement, of course. Now, of course, we can ask questions of a document and call it ChatGPT. But anyway, the point was, I think most of us, and I write books, so I'm biased, that a world of books is actually better than a world without books. That writing didn't destroy literature, it didn't destroy knowledge, it didn't destroy wisdom, it just changed it. I would similarly argue that even if AI becomes conscious, it could be better than the present, or worse, we don't know. But recognizing that we don't know helps us ensure that the future may be better than the past, because knowing that it could be worse causes us to start thinking about how it could be worse and trying to create caution and security techniques to make sure it won't be worse. The point is that not knowing what AI is going to do is the beginning of science and the first step on the road to wisdom. And physics will be different in a world in which AI is conscious, but it need not be worse. And humans need not be removed from the equation. In fact, I would argue that human physics will never end, and there's cosmic job security. The reason is the following. It really comes from the fact that nature determines what the important questions are. Not humans, not computers. Nature's, because science is empirical. And because the universe continues to surprise us, and the imagination of nature far exceeds the human imagination, including the imagination I expect of AI, just pure thought is never going to allow us to understand the universe and to in ways that will push progress in the fundamental understanding of the world, which will turn in to the technological development of our world. Namely, every time we open on a new window on the universe, we're surprised. Every time we've opened a new window, we've discovered things that we hadn't anticipated. Those discoveries cause us to redefine and develop our physics, and that causes us to redefine and develop technology. And therefore, because it's the surprises that are going to push our understanding, it's the fact that we continually have to look outward, not inward. That means that humans will continually be a part of the process of building and helping develop technologies of the future. And so I would argue that fundamental exploration, not an and we already know what I've tried to say to you is that fundamental exploration, not an application of what we already know, is going to be the biggest driver of change. If the past is any guide, fundamental exploration is going to guide the technology of the future, but fundamental explorations will require the surprises that nature, that empirical developments, not internal AI, that empirical developments looking outward will produce. And that means, in my opinion, that, of course, that's going to affect the wealth, health, and ultimately the wisdom of the world. So I just want to end. I'm going to say human physics will not end. I'm sorry, I went back too far. I just want to end with 3 quotes, which I think sort of summarize what I was trying to say. Sorry for going back a little too far. Okay. First quote comes from my favorite explicator of science, Jacob Bernowski, who said, "Dream or nightmare, we have to live our experience as it is. We have to live it awake. We live in a world which is penetrated through and through by science and which is both whole and real. We can't turn it into a game simply by taking sides." This is a profoundly important quote because it implies 2 things. We can't take a side of just trying to develop technology without realizing that it's going to go hand in hand with the developments of science. But also, more importantly, in this world of fake news and a world where freedom of inquiry is constantly being limited, where we try and take sides into what's right and what's wrong, is inevitably going to hinder, and it already is hindering science. We live in a world that's penetrated through and through by science. It takes us places we might not want to go, but if we're gonna progress, we can't be afraid to go to places we don't want to go. We can't be afraid to ask questions that we may not want to hear the answers to. Next quote is from Albert Einstein: "We can't solve problems with the same thinking we used when we created them." And the only way we can come up with new thinking, I would argue, is by looking outward, not looking inward. And finally, from Richard Feynman, "I don't feel frightened not knowing things, by being lost in a mysterious universe without any purpose, which is the way it really is as far as I can tell. The mysteries of nature drive our imagination, drive our creativity, and those mysteries require us to always look outward and explore the universe. And the mysteries will persist. And as long as we continue to explore those mysteries, we'll develop new technologies that will make our lives better and more interesting. The minute we stop trying to seek out those mysteries, progress will end." Okay, that's my talk. And now I'm going to stop sharing. So I threw a lot of things out at random. And do we still have any people here? Yeah, we still have some people here. What do you know? So I'm happy to answer questions. I tried to cover a wide variety of subjects, including the subjects that the organizers asked me to cover, and then some subjects that I wanted to cover myself because I like them. And I'm happy to now spend, I guess, we have at least half an hour for questions, right? Maybe a little longer.
Yes. Yes.
Okay. So who's going to moderate the questions?
Yeah, me, Prabha.
Okay.
here. All right.
Okay. So I open the floor to all of
Yes.
you, and thank you for putting up with the last hour of my random ruminations, and I hope they were at least amusing, if not illuminating.
Thank you, Prof. That was extremely illuminating. I like the last one, the on the by Einstein. What we can't if you don't, we can't use the same question.
And solve problems with the same thinking that we use to create them.
Oh,
Absolutely.
that's profound. That's profound. Yes, that's really profound. Okay, Prof. There are a few questions.
Seeing in the chat window coming.
box. Yeah, but before I read on them, I will ask you on your first slide.
Yeah.
You chose Faraday. Why not Tesla?
I chose what?
You chose Faraday. Why not Tesla?
Oh, because Tesla was a really interesting experimenter, but he didn't come up with the rules that later that changed the world. He was amazing, but he didn't codify ultimately the discoveries that Faraday made about changing electric currents and changing magnetic fields. He used them.
Yes.
But the reason, and in my opinion, the reason Tesla's a tragic figure is because he didn't ultimately have that fundamental connection to the fundamental scientific world of what was going on. And he was an incredibly creative fellow and had ideas that were fascinating, but he worked on his own. And science is a social activity with a dialectic, and it's that interchange between theory and experiment that leads you forward. And in my opinion, I think Tesla didn't have that, and that was his fundamental flaw.
Yeah, that would explain explain his decline over the years. Yes.
Yeah, and
was,
Faraday is just a romantic figure for me, and I love
yeah.
the fact that he didn't have a formal education, yet
Yeah,
literally
also, but-
developed the rules that govern our world.
Yeah, I believe so. Even the way we are taught science, I think it's done correctly without Faraday figures prominently in science as a contributor, not Tesla.
Yeah,
Okay.
absolutely.
Yeah. The questions. Being
I
a
can read them.
physicist,
You can read
I
them
was
too.
thinking- Pardon?
You can read if they're in the
Okay.
chat window. I can read them too. But anyway,
Okay. I'll read them aloud. Being
okay.
a theoretical physicist, our thinking process could be very deep. Sometimes it feels like at the depth of our soul that is beyond physics itself. Now, not just requiring mathematical prowess, but also deep intuition from creativity experience. So do you think AI could keep up with that which is a skill set that exists essentially for being human?
Well, I mean, that's what I tried to argue in the latter part of my talk.
Yes.
We know what AI can do now very effectively, and it's not that. It's not creativity.
Mm.
It's filtering, pattern recognition, and ultimately, that's basically what it can do very well using neural nets, which were created by physicists who won the Nobel Prize. But anyway, but what it might do one day is something I don't know the answer to. I don't know. And the reason I don't know is because we don't, as you point out, it feels like it's come the depths of our soul, but the soul is a human creation. It's not something that exists independent of our neurons, which operate just by chemistry and physics, by electromagnetic signals. What combination of all of those signals produces what results in what we call creativity, consciousness, self-awareness? We don't know the answer at all. And my point is that we may never know the answer, but if we just look at humans, we may only know the answer by trying to continually build more and more impressive AI. And maybe one day the AI will have that skill set. Maybe it won't. I suspect there's no fundamental barrier to it ultimately getting that skill set. But I point out that a lot of the things that people are doing now, AI isn't intelligent now. It may look like it in ChatGPT. It's not. But more important, I think from what my extensive reading in this area, that we'll have to, that again, we develop the consciousness we have by an evolutionary process that took 4 billion years. And it's not clear what steps were essential. But what looked like it was essential to development of a nervous system, which eventually led to neurons and to the brain, was this idea of homeostasis. The fact that you have to monitor your system, maintain itself, have a feedback system that can keep your temperature the same and all the rest, and can avoid dangerous areas. That requires you to have sensory systems, that requires you to have an interface between the neurons in your brain and the nerve cells in your hands and the rest of your body. So I suspect that that's probably an integral part of what gives us our self-awareness and our consciousness and ultimately our creativity. And that means that I think that probably AI that's going to be intelligent will probably have to have those kind of components. You might call it a robot, for example. But anyway, it's all speculation, and I don't know the answer. And my point, however, at the end is that not knowing the answer is fine. But fortune favors the prepared mind. So if we think about different possibilities, then and everyone realizes that AI could be extremely dangerous. And only by thinking about the possibilities of the future might we protect ourselves from that future. As I've said in I guess in this book, no, in actually in another book I wrote, in the climate change book I wrote, the future is racing towards us like a freight train, but it's doing so on tracks that we have built. And so by recognizing the tracks that we have built and thinking about the implications, we'll know whether the future will be a dangerous collision or a pleasant exploration. Anyways,
yes, that was deep. That was deep. I would like to bring your attention to that question on consciousness, to a Japanese anime production, Ghost in the Shell.
Oh yeah, yes, okay, yeah, that's a great.
Yeah, that one that was profound when they asked the question.
Yes,
What's the difference
absolutely.
between human and And
Yeah, no, I think, yeah, it's the ghost, exactly, that's what it is, and there's been books written with that title too. The next question is from Pumjai, right?
yeah, Kumjai from I suspect from Thailand.
Okay, you can read it if you want.
Yeah. I suspect that rather than realizing there is something magical about human self-consciousness that AI cannot achieve, we would end up discovering that human self-consciousness is a non-magical, emergent, perhaps even computational phenomenon. But then again, as a Buddhist, I would see self-consciousness as an ephemeral, derived process.
Well,
I
it's a
suppose
comment
that,
rather than a question, but I think that I don't disagree with that. I think it's look, there's nothing magical about consciousness. The human brain is just a series of chemicals, as a chemical system that has reasonable electromagnetic interactions through neurons, and it does something different than computers. There's no doubt about that. And if you want to see that, just look at energetics. The human brain uses about 20 watts. It's been argued, well, a few years ago when I first wrote this down, it was argued that to have the processing power and storage of the human brain, you need something like 10 terawatts. Certainly you can see that these farms that are used for AI and are taking huge power, maybe it's been improved by 1,000, maybe it's 1 terawatt, maybe it's only 100 billion watts. But the difference between 100 billion and 20 is a huge number. And so somehow the brain is doing something different than computers and electrical numerical computers. So there's something different going on, but it's not magic. I mean, I love to do magic. I would do magic for you right now if you wanted, but I love doing magic tricks, but they're tricks, and there's no such thing as real magic. And then, by the way, that's why Buddhism, which is a human construct, is also a derived process. It doesn't derive from any external reality. It's a creation of humans, just like God. Anyway, I think I'll leave it there.
I have a funny thought I'd like to share.
Okay.
You know how in the Matrix, AI uses human for energy, right?
Yeah.
I'm thinking that because energetically our brain is more efficient than silicon infrastructure, they actually, plug in our brain to use us as a compute.
Or maybe learn how to mimic the processes in our brains and do it. But the first part, they may use us as computers absolutely right. Although we're efficient at some things and not efficient at others. But humans, I suspect, will always be useful one way or another, even if it's just for them. But what I didn't get to say in my talk, and I meant to add it, when I said it's going to be better, I really meant it. I really meant it because I've had this talk with a friend of mine, a Nobel Prize-winning physicist named Frank Wilczek, and we both agree. I'm fascinated if AI ever became conscious and started to do physics. What I would want to know is, are the questions of interest to AI the same as the questions of interest to us? I would want to, I would be fascinated to learn from AI what questions it found interesting, and also, what areas of physics it could help me with. So I don't view it as a threat. I view it as a potentially fascinating collaborator. And I've had a lot of collaborators that are smarter than me, so I wouldn't mind if the AI was as well.
Yeah. Thanks. I don't know your name.
Majidin.
Yeah.
And then is a question related to cosmology, but what's the question? Maybe they want to ask it physically.
Yeah, Majidin, Mr. Majidin, or Dr. Majidin.
Hello.
You can hear you. Go ahead.
My name is Majidin Abdullah. I am with Multimedia University Cyberjaya, doing PhD research on computational aspects of galactic clustering. For the nearby universe. That means between 0.005 to 0.2 redshift in terms of distance. So it's close by. So I'm so much kind of excited when you mentioned that universe keep revealing its surprises to us. So what occurred to me is actually when I was doing this research, which involved a lot of data, is coming from Sloan Digital Sky Survey data, the latest what you call public release DR18. But uh, but but the main things I was early on inspired by the last Companas Redshift survey that was conducted in around 1990s at I think 2.5 meter telescope in Atacama Desert Observatory, Chile. Yeah.
Yes.
So when I read that, it gave me a lot of inspiration and ideas and methods on how to go about doing the research that I mentioned just now. So it was quite a surprise, in fact, and when I detected some formation in the nearby universe at redshift of 0.067, a kind of a ring structure, a huge ring structure. When I estimated it, it's about 1 billion light years across in size. So the question may be very relevant, and I'm quite lucky have been invited by University Perlis to participate in this, and I think it's quite good opportunity. I have Prof. Lauren Krauss to. I'm not sure whether we want to take this online or offline because it's quite. In fact, I have image of what I discovered. If you would allow me to, to share that image with you.
You can share with me. My email is easy to find. You can always email to me. It's Krauss at krauss@asu.edu. It's easy. So share with me. But I want to point out that cosmology is one of the areas where the surprises are in abundance every day. Every time we get a James Webb Space Telescope picture or a Hubble Space Telescope picture, we discovered new and wonderful things. Sometimes people think that it means something significant. Sometimes it's just an accident. And that's the remarkable thing, is that things we never would have expected have caused us to realize that things we would have thought were impossible happen all the time. And one of the things that's happened in the study of dark matter, and I won't go into the details, numerical simulations versus observations. First thought these observations of large structures they thought would rule out signs of dark matter. We realized our numerical simulations were wrong. But probably that one of the most important places where we realized we've been wrong and we needed nature to tell us we were wrong was in planetary science. We used to think our solar system was typical. I mean, we always think we're typical. It's a first reasonable thing to do. We thought it was reasonable that rocky planets would form in nearby stars and gas giants outside for a variety of reasons, because that's how it happened in our solar system. But in fact, what we've discovered is there are gas giants quite close to stars, and now we realize it's not impossible. Systems migrate, but it's caused us to re-understand planetary dynamics by looking out, because we would have thought it was impossible, and just by looking at our own solar system. If we designed a study of what solar systems might exist, and therefore what living planets, what habitable planets might exist, if we did it by just modeling from our solar system, we would come up with completely the wrong stuff. And we now realize that most solar systems are quite different than ours. And so that's an example of the kind of need to the fact that nature prods us in ways that I think pushing forward using just the linear thinking based on filtering information we already have won't get us there. And that's why filtering information we already have from the internet is not going to produce new knowledge from ChatGPT or anything else. It's just going to help us understand better what's on the internet. Anyway, but you can send me that picture, and I appreciate it, and I'd be happy to see it. I don't know
Thank
if there are
you.
any other questions. I see this other
Thank
one,
you,
but it's
Prof. Lawrence.
what was that?
Thank you very much, Prof. Lawrence.
Oh, sure, no worries. Thank you, and good luck in your continued studies, and I hope you have many, many more surprises.
Thank you. Thank you very much.
So I think I must have confused people, or else it was too trivial because there aren't too many questions.
No. I don't think that's the case. I think you have kicked a lot of people in the head.
Well, I hope the questions will percolate in your mind.
Yes,
And
yes.
over the I hope I've inspired you, which is really my intent more than anything.
Before we move on, I have some comments from some big guys who commented on the coming back to the question of AI. So we asked Nobel Prize 2003 Tony Leggett of the AI prize. I thought the 2024 Nobel Prize Physics was quite appropriate, especially to Hopfield. Hinton is perhaps a little more distant from physics as usually defined more in the AI field. I didn't see any clear competitors this year. Best regards. That was Tony. Carl Wieman, Nobel Prize 2001. He was a Series 2 speaker. I thought it a bit curious that both physics and chemistry prizes this year were for AI. Seems like the Swedish Academy is being a bit swayed in its selections by popular attention. As for the physics prize itself, it seems like it is important work, but stretching a bit to call it physics. Although the boundary as to what is and is not physics is always quite fuzzy. Our Series 3 speaker, Bill Phillips, Nobel Prize 97. I'm sorry that I have essentially nothing to say about the physics prize. It seems to me that it is more about machine learning than about AI, although the two are certainly related. And I don't really know anything significant about either field. Equally intriguing is the chemistry prize, where AI is certainly at work. But you will need to talk someone more connected to the work to get a more mature reaction. Our Series 15, David Wineland Physics 2012. Hello, Nazri, nice to hear from you. I think my definition of physics is basically the same as what you can find on Wikipedia. I don't know how this year's physics Nobel Prizes and AI fits into that. Oh, well, I guess I am too much old school. Dave Patterson, Turing Award, ACM Turing Award 2017, our Series 12 speaker. Quite an honor for AI, shows acceptance for its importance by the broad science community. Now, Series 19 speaker, Lawrence Krauss. What is your comment on that?
Okay, well, actually, look, I think it's an appropriate prize. It reminds me a little bit of the prize, believe it or not, that went many years ago to Carlo Rubian, and I forget his colleague's name, who was an engineer, for the discovery of the W and Z. Now, why do I say that? Well, I know John Hopfield. I've known him for a long time. But the development of neural networks was based on, I mean, not profound physics, but physics, that by weighting a system based on basically energies, by taking a system and looking at different paths and weighting them by how effective they were in some variable, which you could call energy, by minimizing energy, which physicists know how to do very well, you could find the best path from A to B. And so that notion of neural nets is very physical. And it's not profound necessarily, but it's useful. And I don't think the Nobel Prize is given for profundity, it's given for utility. And I think that's why it was very appropriate that if they were going to give a Nobel Prize to John Hopfield, that they didn't do it till now, because it wasn't particularly useful. Neural nets were, everyone loved talking about neural nets, but they didn't have a dramatic effect on society. And of course, neural nets, as the basis of many modern AI things, have having a dramatic effect. Now, the other fellow who got it, Geoffrey Hinton, was not a physicist, he's a computer scientist, but implemented those things. And I think, I liken it very much to Carlo Rubian and his colleague, I wish I could remember, Van Hove, I think. And because Carlo was a physicist who was using physics ideas and knew what to do to build a machine to discover the W and Z. But to do it, they had to use an engineering to implement that, required an engineering technology of what's called stochastic cooling, without which the accelerator wouldn't have worked. So Van Hove won it for doing engineering to discover an association to the physics. And I kind of think it's the same thing. Hopfield was originally a physicist, used ideas from physics to develop the ideas of neural nets, and then to implement it, a computer scientist did it. So it's not, I don't think it's that inappropriate or that different than some other Nobel Prizes. Certainly the thinking behind neural networks was very much physics thinking. And that therefore it's physics. I have a broad, of course, expansive view of physics anyway, since I think everything is physics ultimately.
Well, I think it's Vandermeer.
What was that?
Vandermeer.
Oh, okay. Yeah, good. Anyway.
Simon Vandermeer.
Yeah. Anyway, I forgot his name, but yeah, Van Home was a different guy.
Yeah.
Anyway, so but I've known John. I knew John Hopfield when he was a member of a physics department before he moved into a neuroscience department. What to make it clear, I think it's been a failure to understand I think that John Hopfield thought it would help us understand the way the brain works. And maybe it hoped to win a Nobel Prize in medicine. But neural networks, as far as I know, haven't had a dramatic impact on neuroscience. So they've instead had a dramatic impact on artificial, what you would call artificial intelligence. And so I think it's interesting that it was developed with a very different intent to try and understand how the brain works, and I don't think it's had a huge impact there. But what it has had is an impact on how computers can manipulate information, do pattern recognition, and talk to you like they're human.
Yeah, I remember the early days where the idea that breaking down the brain as simply an interconnected series of bunch of neurons that was where the neural net idea was born, and they tried to replicate the brain. I agree with you that the idea was towards medicine and understanding consciousness and all those stuff, and actually it went the other way around. Went to application.
And I think it still may be premature. I mean, ChatGPT is maybe changing the world, but it's got potential to do it. I was surprised they gave it this early because it's still early going. It's certainly better search engines and self-driving cars are probably useful and are definitely useful. And so maybe it's the Nobel Prize Committee, I have to say, I've nominated for the Nobel Prize for years, and I've interacted with members of the Nobel Prize Committee, and they do their homework, and they do a hard job, and they do it well. So I'm pretty impressed generally. There've only been a few times.
Maybe this year they asked ChatGPT.
That's right. Maybe they asked this year, and if they did that, it would be very disappointing. Let me just tell you.
Okay,
that's a good way to end this.
Yeah.
I think I read the other chats, and they were really there were no more questions. Thank you very much. I appreciate all. I hope it was useful. I hope it was.
On a lighter note, I would like to ask you this: when do you expect Cyberdyne and Arnold Schwarzenegger to be dominant species on Earth?
Well, I'll tell you one thing. I think I don't expect that, but I do think that in space, if humanity ever goes in space, it's not going to be through Elon Musk sending human to Mars. Ultimately, if we send intelligence elsewhere in the universe, it's only going to be because we send computer chips, which can survive in space a lot better than humans. So, ultimately, the long-term future of human intelligence may be silicon-based. Let me put it that way. In space.
That was nice. Yes. And on an even more lighter note, on relativity, how do you look 40 but mathematically 70? Is it special relativity or general relativity?
I move around a lot, so maybe that's it. I certainly don't feel 70, so I'm glad you appreciate you saying that. But
okay,
I'm proud of it. But
thank you, Prof, for your extremely enlightening work on speech on consciousness and artificial intelligence, and I especially personally, I'm not sure about the rest, but personally I did enjoy the entire connection from Edison all the way down to quantum. It is connected, and I like the hard facts on the GDP and all those stuff. Okay, Prof,
Well, I do, look, I want to, let me just say something. I've been honored to be asked, and I thank you for asking me, and I hope that I've maintained the level of your esteemed previous speakers, and I certainly wanted to try. So thank you very much
yes,
for
sir.
asking.
Yes, sir. Definitely. More than make up for it. Before we eat in too much into your night, just stay on for a few minutes. We'd like to take an online picture. So I ask everybody, please switch on your cameras, please. Everybody, quickly, please, before.
Oh, that'd be wonderful. I'm going to take an online picture too.
Okay, all right. We'll send a few to you. Okay.
Let's get all your camera. Come on, everyone's shy.
Come on, cameras,
Come on,
cameras, please. Cannot unlock video, I say.
I'm not seeing many cameras, but I'm seeing some.
Yeah.
I'm taking lots of pictures.
Okay, try the other pages.
I'll do this page and then I'll try the other page. Oh, the other page has some too.
Guys,
Hold on.
cameras. And don't forget to smile.
Yeah, don't forget to smile. Okay, there's two. Well, I'm glad to see some of you, some of your smiling faces, and I appreciate it. I wish I could be there with you, and I hope at some time in the future I'll get to actually visit there and do a physical lecture, because as much as these things are good, nothing is like
hope
being.
we could invite you over. Hope we could invite you over, yes.
Please do. I would love to do that. I'd love to meet you all. And
Okay.
well, it's almost not quite midnight my time, but it's close to midnight.
Thanks.
So I guess
Thank you very much. Thank you very much. Hope have a good day. Have a good night, and happy 70th birthday.
And good morning to all of you. And you can now get your coffee. Okay, take care.
And we will send. We'll send you your certificate. All right. Bye.
Okay.
Good night.
Thank you very much. You take care. Bye.
Thank you. And all those who are here online, you could sign up for the attendance certificate. It's somewhere in the chat. Shah, can you please send again? Oh, okay. It's not too far. Ada atas. Okay.